Hello. Hi to all of you. Again, I welcome you to our third session. Our today's session is about Fourier integral, and we are proceeding on our course, MS 8102 Engineering Mathematics 2 and MS 8122 Advanced Calculus for Electrical Engineering and MS 8102 for Mechanical Engineering. Our session 3 today is about Fourier integrals. We have seen in our session 1 the introduction to Fourier integrals, properties and characteristics, the way they behave, even functions and odd functions in finding the areas. And in session 2, we have seen also the way even in odd functions, they work together in cosine and sine while representing functions, especially periodic functions or continuous functions, under the symmetric region using Fourier series. So today we are going to see how Fourier integrals are used to represent the function f of xc. Now, we see that what is Fourier integral? Just this is a way Fourier integral is used to represent a function f of x, which is now continuous. In session 2, we saw that we can represent a Fourier series to a function f of x within the region of symmetry. But Fourier integrals now are used to represent a function f of x, which is stretching from negative infinity to positive infinity. So we say Fourier integrals, these integrals used to represent a function f of x, a function f of x, which stretches from negative infinity to positive infinity. And the function f of x must obey the Dirichlet condition. And the function f of x must obey the, say, Dirichlet condition, which states that this function states that have the major one says, this one says it must stretch from negative infinity, that is a function f of x must be continuous from negative infinity to positive infinity. And the second one, the function f of x must not be periodic, neither step function, neither a step function, nor a discontinuous function. And the third one, the function f of x must obey the condition that must obey the condition or the fact that when you integrate from 0, from 0 to to pi sine of omega over x equals to pi over 2. This is with respect to x. This is with respect to x. Respect to x equals to pi over 2, and this is infinity, from 0 to infinity. From 0 to infinity. All right. So this is a very important thing. First, it must stretch from negative infinity to positive infinity. And the second one must not be periodic, the function f of x. Neither should it be a step function nor a discontinuous function. And the last one must obey this condition. So let us see how we can use this function, this Fourier integral. We say the Fourier integral, Fourier integral is given as the Fourier integral f of x equals to 1 over pi when we integrate from 0 to infinity of a omega cosine omega x plus b omega sine omega x with respect to x. This is how the function f of x is given as the Fourier integral, where a omega is given by the integral from negative infinity to positive infinity of f of x cosine of omega x with respect to x, and b omega is given by the integral from negative infinity to positive infinity for a function f of x multiplied to the sine omega x with respect to x. So this is how the Fourier integral can be used to represent a function f of x, that is 1 over pi, the integral from 0 to infinity of a omega multiplied to cosine omega x and added to the b omega multiplied to sine omega respect to omega. We call these a omega and b omega, these are defined as the Fourier integral constants or coefficients. So we say not a omega and b omega are known as the Fourier integral coefficients. Fourier integral coefficients. So let us see an example. Let us see an example on how to find the Fourier integral. Example, find the Fourier integral representing the function f of x given by f of x equals to 0 for x less than 0, then 1 for 0 is less than x is less than 2, and 0 for x greater than 2. Okay, now looking to this question, we can see that this function f of x stretches from negative infinity to positive infinity. So it is continuous and it is not a step function. It is continuous. It stretches from negative infinity to positive infinity. And so it is not copying and repeating itself. It stretches from negative infinity to positive infinity. So we can, the first thing to understand or to see how it looks like, we need to sketch this function f of x. So let us see how it looks when we sketch it. So solution, we say sketching. Let us sketching the function f of x. Let us sketch and we will see that. So we have this is say 1 of 2 of 3. This is x and this is y. So negative, say -1, and the value of y 1, say this is 2, and we says from all values which are less than 0, yeah, less than 0, and from 0 to 2, this is 1. From 0 to 2, the value of f of x is 1. From 0 to 2, the value of f of x is 1, you can see here. And from 2, the value of f of x is 0. So you can see these intervals that from negative infinity to 0, the value of f of x is 0. From 0 to 2, the value of f of x is 1. And from 2 to positive infinity, the value of f of x again is 0. Now, these intervals are very, very important since we know that f of x is given by 1 over pi, the integral from 0 to infinity of a omega cosine omega x plus b omega sine omega x with respect to omega, where a omega equals the integral from negative infinity to positive infinity of f of x cosine omega x with respect to x. B omega equals to the integral from negative infinity to infinity of f of x sine omega x with respect to x. So let us see how we can get these values for a omega and b omega using these intervals and the integrals given. So we say, let us start with now. Let's start with a omega. We say that a omega equals to the integral from negative infinity to infinity of f of x cosine omega x with respect to x. So we can break this according to the intervals given. So this one equals to the integral from negative infinity to 0, f of xc cosine omega x with respect to xc, plus the integral from 0 to 2, yes, of f of xc cosine omega x with respect to xc, plus the integral from 2 to positive infinity of f of xc cosine omega xc with respect to x. But from the intervals, we see that from negative infinity to positive, from negative infinity to 0, the value of f of xc is 0. From negative infinity to 0, the value of f of x is 0. So multiply by cosine omega xc plus, and we see that from 0 to 2, the value of f of xc is 1. The value of f of xc is 1. Add here the integral from 2 to infinity. The value of f of xc from when x equals to 2 to infinity, the value of f of xc is 0. So you multiply with cosine omega x. So you see that this is 0 and that one is 0. So the value of omega x now remains here. We can evaluate the value of omega x from 0 to 2 cosine omega x with respect to x. So integrating now the value of cosine omega x with respect to x, when we integrate cosine omega x, we get sine omega x from 0 to 2. Now, substituting this one, evaluating the value here, we get, when we substitute sine, when x equals to 2, you get sine 2 omega. And the value, integrating this one, you get 1 over omega. Here there is 1 over omega sine x. So this one is 1 over omega. And the sine, when you substitute 0, is sine of 0, which is just 0. So this is the value of a omega, which is 1 over omega sine 2 omega. This is the value of a omega. So let us see the value, what will be the b omega. B omega is given by the integral from negative infinity to positive infinity f of xc sine omega xc with respect to xc. So we can now break this integral with respect to the intervals given to the equation or the function f of x. That is, we can integrate from negative infinity to 0, where the value of f of x is indifferent. Add from 0 to 2 f of x multiplied to sine omega x with respect to x. Add from 2 to positive infinity f of x sine omega x with respect to x. Now we know the intervals. The intervals from negative infinity to 0, the value of f of x is 0. So multiplied to sine omega x, plus the value from 0 to 2, the value of f of x is 1. You multiply by sine omega x with respect to x, plus the value from 2 to positive infinity of f of x is 0 multiplied to sine omega x with respect to x. Right. So here you see this is going to be 0, and the last one is going to be 0. So b omega here is the integral of sine omega x with respect to x, which is now integrating from 0 to 2 integrating, you get negative cosine omega x over omega, from 0 to 2. So substituting the value of x, you get a negative cosine 2 omega minus cosine of 0, cosine of 0, multiplied the whole of it by 1 over omega. Now this is negative 1 over omega, the bracket, cosine 2 omega minus 1. So this is, so b omega equals to, when you open brackets here, you open bracket by negative, you get 1 omega. This will be bracket 1 minus cosine 2 omega. So this is the value of, or we say the Fourier integral coefficient for b omega. We have the a omega already. The a omega we have here. We have a omega. We saw that our a omega is 1 over omega sine 2 omega. That is our a omega, 1 over omega sine 2 omega. And our b omega is 1 over omega 1 minus cosine 2 omega. So let us see how will be the function f of x. Now, our function f of x is given by, 1 over pi, the integral from 0 to infinity of a omega cosine omega x plus b omega sine omega x with respect to omega. So our a omega, what is our a omega? So we have 1 over pi, the integral from 0 to infinity. Our a omega is 1 over omega sine 2 omega cosine omega x plus, and our b omega is 1 over omega cosine, this is 1, sorry, this is 1, this is 1 minus cosine 2 omega sine omega x d omega. All right, so we know that sine 2 omega equals to 2 sine omega cosine omega, and 1 minus cosine 2 omega, this equals to sine, sorry. This is sine, this is the sine, this is sine square omega. You know, this is from half angle. This is from half angle. We have this. We say sine square. Remember, sine square x equals to a half 1 minus cosine 2 x. So multiplying here, we have sine square x equals to 1 minus cosine 2 x. So it is the same as saying sine square omega equals to 1 minus cosine 2 omega. So you see, 1 minus cosine 2 omega is the same as 2 sine 2 omega. So, okay, now substituting there, so we have 1 over pi, integral from 0 to infinity, sine 2 omega over omega. This is going to be 2 sine omega cosine omega xc over omega plus, and this is 1 minus cosine 2 omega is 2 sine square omega. So we have 2 sine square omega sine omega xc over omega with respect to omega. So we see here we have 2, so we can factor out 2. So factoring out this is 2, we have 2 over pi, the integral from 0 to infinity. And we have here sine omega over omega, sine omega over omega. You can also factor out sine omega over omega. You remain here with, this is 2 sine omega cosine sine omega, we have here cosine omega. So we remain with cosine omega x. We have minus somewhere. Yeah, this is, we have minus somewhere. Yes, we have minus somewhere here. For b omega, we have negative. We have negative for b omega. We have negative for b omega. For b omega here, we have this one here. This one is negative. For b omega, this one is negative. Yeah, this one is negative. And where also? Here. This one is negative. So this is negative. So minus, yes, sine omega x with respect to omega. What is this? From this fact, that cosine of a plus b plus or minus b equals to cosine a cosine b minus or plus sine a sine b, sine a sine b. So if it is like a, if a equals to b, and we wanted to use for plus, we say cosine of 2a equals to cosine a cosine b minus sine a sine b. So this is saying cosine 2 omega equals to cosine 2. We have this one. We have this cosine. We have, sorry. This is not true here. This is not true. This one and this one. So we have here, if we have this cosine omega x minus sine omega x, here we'll have cosine omega plus omega x. This is what we have here. So this is 2 over pi, the integral from 0 to infinity, sine omega over omega, and here we have cosine to the bracket omega. This is omega plus omega x, whatever. This is omega plus omega x with respect to omega. So this is our Fourier integral representation for a function f of x. A function f of x now has been represented as a Fourier integral, but now this is the integral f of x equals to 2 over pi, the integral from 0 to infinity, sine omega over omega. This is multiplied to the cosine of omega plus omega x with respect to x. This is how we can represent a function f of x. You remember that function f of x, which stretches from infinity to infinity. Now this has converted it to 0 to infinity, and you can see here the two. So this is how we can write or represent a function f of x using the Fourier integral representation. Sometime you can be asked to find the Fourier cosine integral or the Fourier sine integral. Let us see what are these ones. The Fourier cosine integral and the Fourier sine integral. So let us see the Fourier, start with Fourier Fourier cosine integral. Fourier cosine integral. Fourier cosine integral. We say this is nothing but the Fourier integral representation when the function f of x is even. So we say this is the Fourier, the representation of, this is the representation of a function f of x, a function representation of a function f of x, a function f of x, using Fourier integrals, but when f of x is even. When f of x is even. We know that, hence we know that a function f of x is given by 1 over pi, the integral from 0 to infinity, a omega cosine omega x plus b omega sine omega x with respect to x, where a omega equals to the integral from negative infinity to positive infinity of f of x cosine omega x with respect to x, and b omega is given from negative infinity to positive infinity of f of x sine omega x with respect to x. Now, if f of x is even, you remember the behavior of the even and odd function when you multiplied it to another function. You remember that cosine, remember that always cosine, the function cosine of f of x is even, and sine x is odd, an odd function. So when f of x is even, this means a omega will be equal to the integral from negative infinity to infinity f of x cosine omega x with respect to x will be equals to twice from 0 to infinity, since this is even and this is even. So even times even is even, so it will be an even function cosine omega x with respect to x. So this is how omega, the Fourier integral coefficient a omega will be given. And b omega will be equals to from negative infinity to positive infinity f of x sine omega x with respect to x will be equals to 0, since this is even and this is odd. So odd times even function is an odd function. Therefore, how will it look like, the function f of x? The function f of x now, you just will be the integral from the 1 over pi and the integral from 0 to x. A omega will be there. A omega will be there, cosine omega x. Now b omega, since it is 0, then we'll end up there. So this is the Fourier cosine integral. This is the Fourier cosine integral will be obtained using this formula. F of x equals to 1 over pi, the integral from 0 to infinity, a omega of cosine omega x with respect to omega. So this is how the Fourier cosine integral will be given. And let us see the Fourier sine integral. Let us see the Fourier sine integral. The Fourier sine integral. Fourier sine integral, this is nothing but the Fourier integral, the representation of a function f of x using Fourier integral. But now when a function f of x is odd, we say this is nothing but just the representation of a function f of x using the Fourier integrals, Fourier integral, when a function f of x is odd. Again, we know that a function f of x is given by 1 over pi integral from 0 to infinity of a omega cosine omega x plus b omega sine omega x with respect to omega, where a omega is given by the integral from negative infinity to positive infinity of f of x cosine omega x with respect to x, and b omega equals the integral from negative infinity to positive infinity of f of x sine omega x dx. So when f of x is odd, we say when f of x is odd, and we know that cosine x is even and sine is odd, so say a omega will be the integral from negative infinity to positive infinity f of x cosine omega x with respect to x. So you see, this is odd and this is even. So odd times even is odd, so it means a omega will be equals to 0. What about b omega? B omega will be equals to integral from negative infinity to positive infinity f of x sine omega x with respect to x. See here, this is odd, and the sine is always odd. So odd times odd is even. So b omega now will be equals to twice integral from 0 to infinity of f of x sine omega x with respect to x. So when evaluating the Fourier sine integral, this is the formula will be used to find the b omega, and thus the function f of x will be equals to, when you multiply there, will be equals to the integral of 1 over pi now from 0 to infinity. Here we have b omega, sine omega x with respect to omega. So this is how the Fourier sine integral will look like. Up to this point, let me say thank you very much for today's session. And the next session, session 4, session 4, we will discuss on the multiple integrals. Multiple integrals. The next session will be on the multiple integrals, and we will see on the double integrals. Here we'll start discussing about double integrals and triple integrals. So we'll start with the double integrals. We'll see what are double integrals and see some examples in evaluating double integrals. We'll go to even other representations using Cartesian and polar coordinates used in double and triple integrals. So up to a point, thank you very much. See you next session.